Good evening, everyone. Welcome back. It is our November Speakers Night for 2024. This is actually the last one for 2024. Very exciting. Welcome to RASC Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of RASC Toronto Centre. This is our Speakers Night presentation. Please note that this meeting is an online-only presentation and not at our new York University meetup location. Our president, Tom Luton, will be talking about our various programs later on this evening. But first, we have our very special event to kick off. So, to get us started, we're going to go ahead and begin with a land acknowledgement. The Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. So, as we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. So going on to our speakers night part, I get to introduce our fantastic speaker. I'm very, very happy to be able to bring you this evening Claude Cournoyer-Cloutier, a PhD candidate in astrophysics at McMaster University. This is her final year of studies, and she's already received a MSc or a master's from McMaster in 2021 and a Bachelor of Science in Physics from McGill in 2019. Her research focuses on some of my own favorite topics, so I'm a little bit biased, computational studies of star formation, and in particular massive binary stars and the dense, massive clusters of stars in which they are born. So Claude has a lot of outreach experience as well in astronomy, physics, and history, and she's currently working on all kinds of things, including, of course, McMaster's on-campus portable planetariums, which sound super, super fun. She's involved in a lot of EDI initiatives, loves traveling. And from my own knowledge, I have to say she also had a really excellent poster at Casca this year. So massive binaries, massive clusters sounds like massive fun to me. I am not sure. I am totally sure that I'm not the only one really excited for this one. So Claude, please take us away to this star-studded affair.
Thank you for the kind introduction, Elena, and I'm absolutely delighted to be here with you tonight and to talk about some of the topics that I find most exciting in astronomy, that is binary stars and star clusters. So over the next 45 minutes or so, we're going to go on a journey together, starting from our own location within the solar system and moving outwards towards the outer regions of our own galaxy and even beyond. And throughout that journey, we'll talk a lot, to be fair, about binary stars and star clusters. We'll go over some basics, but I'm also going to share some new and exciting research with you, some of which is my own, some of which is my collaborators, and some of which is just new and exciting. So you may wonder why I'm starting with pictures that are obviously not astronomy. And the reason for that is simple. It's because wherever we are on the surface of the Earth, no matter the time of year, there is a very clear point in common. It is the fact that if we look up at the sky, we will see at most one star. We will see the sun. But planets in our own solar system, including the Earth, only have one sun, only have one star. And that is very, very obvious, again, when we look at the sky. But that is not the case for all planets in our galaxy. In fact, roughly half, if not a bit more, of all stellar systems within the galaxy are made up of two or more stars. And so an outcome like the one we see on the left from this image taken from a Star Wars movie is actually quite likely. Planets orbiting binary stars, or planets being in systems where there are two stars, are in fact quite realistic and quite plausible within our own Milky Way. The image on the right, I've also chosen it to highlight the differences between the night sky we see on Earth and the night sky we would see if our planet was located in a very different place in the Milky Way. So this specific image is a mock-up of what the sky would look like if the Earth was located within a globular cluster. Globular clusters are among the most massive and densest objects within our galaxy. They are very dense clusters of stars containing hundreds of thousands, if not millions, of stars within them. And if our own solar system was located within such a dense cluster of stars, the night sky would look a bit like the image we see on the right. And so it would be radically different from what we see today when we look up at the sky. In fact, such a night sky would make it very, very hard for us to even do astronomy because the sky would be so bright and so crowded at night that we would be almost unable to see beyond this star cluster. And so all of that is to say that the location of the Earth within the Milky Way, the fact that it is not within a cluster of stars, is useful for us when we do astronomy, but it also means that in some ways the sun is not quite your typical star. In other ways, however, the sun is very much a typical star. And because of that, it's going to be our first stop in our trip through the Milky Way. So you can now see a telescope image of the sun up on your screens. Sorry. As you can see, the surface of the sun is active. It's definitely not as smooth as what we might expect. That is because the sun is extremely hot. It's radiating away energy. I also want to highlight what you can see on the top left of your screens right now, which is the distance in light minutes between us and the sun. I'm going to have that up as much as I can just to give you a sense of how far away different objects that we'll look at together are located. So a distance, just as a reminder, a distance of 8 light minutes means that it takes 8 minutes for the light to travel from the sun to us. And so if anything happens at the surface of the sun, we can only ever learn about it 8 minutes later. Now, in terms of its size and mass, the sun is a very average star. So it's now shown to scale alongside stars that are much smaller and stars that are much larger than the sun. The little red blob you can see in the bottom left corners of your screen is a type of star called a red dwarf or M dwarf stars. Those stars can be as small as barely 8% of the mass of the sun, and you can also see that in terms of size, they can get quite small and quite compact. On the other end, if you turn your attention to the top right of the screen, you can see one massive star. Those stars are much hotter than the sun, much more massive, much more luminous. We're talking about tens of thousands, if not hundreds of thousands times the luminosity of the sun. So they are very, very different than the sun, and they also tend to have short, eventful lives. On the other end, stars less massive than the sun tend to be unchanging over billions and billions of years. And so between those two extremes sits the sun, and sit stars that are like the sun, that are typical star like most stars within the Milky Way. That, however, is not the only way in which the sun is fairly average. The sun is also fairly average in terms of its age. The sun is about 4.5 billion years old, and for a sun-like star, this is very middle-aged. We can expect the sun to live a total of about 10 billion years. And so in that way as well, the sun has so far evolved fairly typically of a star like itself. But one way in which the sun is either slightly atypical, or at least not specifically typical, is the fact that the sun is within a solar system or within a stellar system with only one star. And that is not the case for most stars within the Milky Way. And in fact, it is not the case for our closest neighbor either. Most stars within the Milky Way are part of what we call a binary system. So such binary systems are pairs of stars that are in orbit around a shared center of mass. As you can see on the video, it means that both stars appear to be rotating around a fixed point in space, and they remain close to one another throughout their entire orbit. And so throughout the talk, every time I talk about a binary star, this is such a pair of stars that I'm referring to. Two stars in orbit around the shared center of mass that are moving through space together. As I mentioned about a minute ago, binary stars are extremely common in the universe. Within our Milky Way, about half or slightly more than half of all stars are in binaries or higher order systems, by which I mean they can also be, for instance, in triple systems. And that is, in fact, the case of our closest neighbor. So the stellar system that is closest to us is a triple star system made up of Alpha Centauri A and B, which are shown here in the top right of the enlarged image. They're both together within that blue blob. And those two stars, which are a fairly close binary, form a triple system with Proxima Centauri, which is shown at the bottom right of your screens. Proxima Centauri is the star that is closest to the Earth, aside from the Sun, of course, but the star that is closest to the Earth right now. But as it orbits around Alpha Centauri A and B, through hundreds, if not thousands of years, at some point, Alpha Centauri A will be closer to the Earth than Proxima Centauri is. Those stars are visible from the southern hemisphere, but not from the northern hemisphere. So some of you may have never seen them with your naked eye. But you can see on the left where they would sit in the sky compared to some well-known constellations. In terms of sizes, the stars making up the Alpha Centauri and Proxima Centauri system are actually quite typical. So just for your reference, you can see the Sun, which is in size the third one from the left, and at the very bottom right, you can see the size of Jupiter, which is the largest planet within our solar system. If I pull up the three stars from the Alpha Centauri system, you'll see that Alpha Centauri A is just slightly bigger than the Sun, Alpha Centauri B just slightly smaller, and Proxima Centauri finally is barely larger than Jupiter. And that is because Proxima Centauri is a so-called red dwarf or M dwarf star, which is only a tiny fraction of the Sun's mass. Alpha Centauri A and B, on the other end, are very, very similar to the Sun. In terms of their masses, Alpha Centauri A is about 1.1 times the mass of the Sun, while Alpha Centauri B is 0.9 times the mass of the Sun, so just nicely bracketing the Sun in terms of mass. There's a larger difference in brightness or luminosity than there is a difference in mass, though. Alpha Centauri A is 1.5 times as bright as the Sun, and Alpha Centauri B only half as bright as the Sun. And just to illustrate this point, I'm going to pull up a slightly more technical graph on the right-hand side. So all the little black dots you see on this screen represent stars that we've observed within the Milky Way. So regions with high densities of black points are regions in which stars commonly sit, whereas regions without those black dots are just regions of parameter space in which you don't see stars. For the axes, the vertical axis represents how bright a star is, with the Sun being defined as 1. So for example, the number of 1 million at the very top means that a star is 1 million times as bright as the Sun. And the number of 1/1000th at the very bottom means that a star would be 1/10,000, of the luminosity of the Sun. The horizontal axis on the other end represents the temperature. And so looking at where the black points sit, you can see that in general, stars that are hotter also tend to shine much brighter, whereas cooler stars also tend to be dimmer. Proxima Centauri is a textbook case for a star that would be cooler and dimmer. As you can see, it sits almost at the bottom right of this diagram. On the other end, the Sun sits at a brightness of 1 and a temperature of about 5,700 degrees. Alpha Centauri A, just slightly brighter and slightly hotter. Alpha Centauri B, slightly dimmer and also slightly cooler. This system, however, is not the only nearby binary system. Another well-known example is is within a group of stars that many of you may know as the Big Dipper, which is now up on the screen. So you can see several bright stars at the center of the image. But if you squint, or if you already know about this, you may see that the second brightest star from the left is in fact two close stars. And if you have good vision, good eyesight, and you're lucky enough to be somewhere with little to no light pollution, you may be able to see with your naked eyes two stars at that location within the constellation. Those two stars are called Mizar and Alcor, and we've known for thousands and thousands of years that those two stars are there, because again, they are visible with the naked eye. What we figured out more recently, however, is that those are not two stars, but six stars. Mizar itself was first found out to be made up of Mizar A and Mizar B, and further studies with better telescopes and better techniques eventually revealed that both Mizar A and Mizar B were in fact close binaries. So a star that we've believed for a long time to be just one star has turned out to be four stars, two binaries in orbit around each other. And similarly, Alcor has also been revealed to be in fact a close binary system. And this is something I always like to bring up when we talk about how ubiquitous binaries and stellar multiplicity are. Because even though we've known for a long time about so-called double stars, better telescopes and better observing techniques actually reveal that they're even more ubiquitous than we thought. And this system of stars is still actively studied today. In fact, it is still actively under debate in the scientific community whether Mizar and Alcor are bound together by gravity, making this a sextuple stellar system, or whether they are in fact separated. And so that really highlights how even things that could appear obvious at first glance can be in fact quite hard to puzzle out in astronomy. Now, we've just talked about several binary systems and in fact talked about how we can discover such systems. It would be interesting in that case to know what kind of techniques we can use to both detect and characterize those binaries. The first and most obvious one is using something called astrometry, which is looking at the motions of the stars in the sky. So looking at the same video we used earlier, we can trace out the motions of the two stars. Now, imagine that those stars would have that same configuration within the plane of the sky and would be close enough that we can see them as two separate sources. If that were the case, it might be possible by taking several telescope images over days or even years to trace out that motion of the two stars. That can only happen, though, if you're fairly lucky in terms of the distance to the binary system and its orientation. In most cases, you might have to use slightly more sophisticated techniques. One of those techniques relies on one of the star eclipsing the other or hiding the other behind it. Such binaries are often called eclipsing binaries. And you can see from the video now playing on your screens what happened in such a case. So let's say we have a slightly bigger, slightly brighter star, which is in orbit with a slightly dimmer, slightly smaller star. When the large star completely obscures the smallest star, we see a large dip in brightness because we're completely losing out the contribution from the smaller star. On the other end, when the smaller star passes in front of the bigger star, we only have a slight dimming because we still see most of the brightness, but the smallest star is not quite as bright as the larger star. And in such a case, looking at the variation in brightness through time and seeing that this is a periodic signal that comes back again and again, we can figure out that the two stars are part of the binary system just by relying on the variation in their light curve. The last technique that is commonly used and that is slightly more complicated relies on something called spectroscopy. So spectroscopy is a measure of the amount of light that we observe in each specific wavelength or each specific color coming from the star. And that technique is intrinsically tied to chemistry and studies of chemistry we can do in labs, chemistry and physics, because each element has its own signature, has its own exact wavelengths at which it will absorb or emit light. And so such a technique can be used to understand the composition of stars, but can also be used to understand whether stars are moving away from us or towards us. Because we know very well at what exact colors or what exact wavelengths we should see a star's signature, if the entire pattern is shifted slightly towards the blue or slightly towards the red, that gives us a very clear indication that the star is moving either towards us, if colors are bluer, or away from us, if colors are redder. And you will see from the animation on the right-hand side just how that plays out. So for example, you can see the red star moving away from us, and so its lines are moving in one direction, and as it moves towards us, the lines are shifting in the other direction. And so that, if we see that signal coming from one or two stars, that gives us a very, very clear indication, once again, that the stars are in a binary. And so all in all, we have a variety of techniques that we can use in order to detect and then characterize binaries to understand how large the separation between the two stars is, and also what are the masses of both components. One more thing I want to highlight in this section, and we're now looking at a fairly recent plot from the scientific literature, is a broader discussion of how common, how ubiquitous stellar multiplicity is. And so those are measures of the fraction of stars that are single, that are in a binary, in a triple, etc., within something called the galactic field. The galactic field is the parts of the Milky Way in which most stars sit. This is within the disk of the galaxies, and those are the regions of the Milky Way that are fairly unclustered. The Sun, Alpha Centauri, Proxima Centauri, for example, all sit within the galactic field. And within that galactic field, the fraction of stars that are in binaries is a very, very strong function of the mass of those stars. For stars like the Sun, for example, which are shown in the plot completely on the left-hand side, just above the little 1, for 1 times the mass of the Sun, you can see that about 60% of such stars are single stars, like the Sun. About 30% of them are in a binary system, and about 10% of them are in a triple system, like Alpha Centauri A, B, and Proxima Centauri. On the other end, if you turn your attention to the right of this plot and look at stars that have a mass of 20 or 30 times the mass of the Sun, the picture we see there is strikingly different. In particular, we see that the triple and quadruple star fractions are both above 30%, and together they make up about 80, slightly more than 80% of all systems. In other words, if you are a massive star, you have an 80% chance of being in at least a triple system, slightly less than 20% chance of being in a binary, and it is extremely, extremely unlikely that such a star would be single. And so we have behavior that is extremely, extremely different from what we see for Sun-like stars. And so the two key takeaways here are, for Sun-like stars, it is fairly likely that you will be either single or in a binary. Whereas for massive stars that are more than 20 or 30 times the mass of the Sun, even stars more massive than 10 times the mass of the Sun, we should always think of those stars as being in a binary by default, because it is much more likely for those stars to be in a binary or a triple than it is for them to be in a single star system. Now that we've set the stage for binaries, we can turn our attention to the second piece of our puzzle for today, which is star clusters within the Milky Way. So the Milky Way is a spiral galaxy, a bit like the one that I just started showing on your screens. Those spiral galaxies are made up mostly of a disk that is actively star forming, and that is most of the image that we see, as well as a diffuse stellar halo. Within the disk, within the star forming regions in the disk, all the little pink pockets you can see on the image correspond to regions that are actively forming massive stars. And most of those regions are in fact actively forming star clusters, like this one. And so what happens in those regions is that you take all the gas within the region, let it collapse under the effects of its own gravity, and then start forming stars. As the newborn stars um, affect the nearby environment through radiation and through stellar winds, they evacuate the gas and stop star formation within the cluster. And so in the image on the left, you can see that those newborn stars have started carving out cavities within that gas and clearing out the nearby gas. And we can see both the gas at the bottom left and the stars at the top right in the image simultaneously. And this is an image of a cluster that is very young, at least in terms of astronomical ages. It is only a few millions of years old. On the other end, very old, very dense star clusters, like globular clusters, are completely devoid of gas because they formed billions of years ago. Just to give you a sense of scale, this is more than 1,000 times older than the cluster I was showing on the left. Those are also extremely massive star clusters that contain hundreds of thousands, if not millions, of stars. And those tend to be located in the outskirts of their host galaxies, which is why I'm showing it here to be kind of at the bottom right from just this tiny speck of light. And the Milky Way is known to host both young clusters and old globular clusters. In fact, it hosts about 150 globular clusters and a range of young clusters going from the small to the decently big. And we'll explore somewhat both of those over the second half of this talk. The closest region to us that is currently forming massive stars, and in fact most likely the closest star cluster to us, or one of the closest star clusters to us, is the trapezium cluster located within the Orion Nebula. And you can now see on your screen a very recent image of the Orion Nebula cluster, or the trapezium cluster, taken with the James Webb Space Telescope. Just to give you a sense of scale, this is located about 1,500 light years away, and you can see the little line that I drew on the top left of the screen showing what about 0.4 light years corresponds to. So that gives you a sense. For example, the stars within the very center of the image, as we zoom in, are much, much, much closer to one another than we are to Proxima Centauri or Alpha Centauri A and B. Those stars are interesting for several reasons. Part of it is that they are among the closest massive stars to us, if not the closest massive stars to us. And if you remember our discussion from a few slides ago, you may remember that massive stars are virtually always in binaries. And that is the case, indeed, for those massive stars in Orion. And so the first star that I'm going to highlight here is one of the stars making up this trapezium cluster, which are the four brightest stars you can see in the center of the image. And from right to left, they are labeled A, B, C, and D. And the first one I'm highlighting here, Theta Orionis A, is in fact a triple system. So although it appears to be only one star, even in this very, very high quality image, we know from observations done, for example, with spectroscopy, that this is in fact three stars. We have an inner binary where the two stars have masses of 15 and about 2.5 times the mass of the Sun. And the separation between those is the same as the separation between the Sun and the Earth. So they are really, really quite close in terms of distances between stars. The third star, the outer companion, is located 500 times further away. So we have a system that is highly complex in its structure. The second one here, Theta Orionis B, is in fact a quintuple stellar system. So there are 5 stars in that part of the trapezium cluster. The 2 inner ones have 6 and 2 times the mass of the Sun, and that binary is likely fairly stable. The 3 other companions, which are less massive, appear to be bound to that binary for now, but the general expectation is that they will not remain bound to them for long because they are located in a region of high stellar density, and nearby stars should be able to disrupt that system over the next mega year or 2 mega years. The brightest star right here, Theta Orionis C, is a binary system. It's made up of one star that is 33 times the mass of the Sun and one that is 11 times the mass of the Sun. And that star is the main source of energy within the trapezium cluster. It provides most of the luminosity, most of the stellar wind. Because if you remember from earlier in the talk, we can see that luminosity increases a lot faster than mass. So although the most massive of the two, the one that is 33 times the mass of the Sun, is 3 times more massive than its companion, it's probably about 100 times brighter, or at least a lot more than just 3 times brighter. The last quote-unquote proper trapezium star, Theta Orionis D, is thought to be probably a single star, but you may notice the question mark. And that is because we know that there are several nearby stars that may or may not be bound to Theta Orionis D. So even though it might not be strictly in a binary, it is still in a region with very high stellar density. And finally, this slightly fainter star here is also a binary. It's made up of 2 stars that have masses just below 3 times the mass of the Sun. But the striking thing about this binary is how short its orbital period is. The 2 stars orbit each other within 10 days, which means that it's an extremely quick orbit, and they're also very, very close to one another. Another well-known and interesting region within the Milky Way that is actively forming massive stars and also several star clusters is the Carina Nebula. And so we're now looking at images taken by the European Southern Observatory of the Carina Nebula, which is located in the southern hemisphere. And it's also quite a bit further from us than the Orion Nebula was, so about 7,500 light years away. One of the reasons why the Carina Nebula is well known is because of the star Eta Carinae. So I'm going to highlight it briefly on your screens. There you go. And Eta Carinae, which is shown mostly on the left, is very well known for the great eruption it has undergone in 1843. So before that point, Eta Carinae was not visible to the naked eye, but suddenly in 1843 it became visible, and in fact it became the second brightest star in the sky. And that is due to the fact that Eta Carinae is a massive star. It started its life at likely more than 150 times the mass of the Sun. So it is and was really a huge star, extremely bright. And those stars tend to have very short and very violent lives. I often say it as the fact that big, massive stars live fast and die young. And so the lifetime of such a star is barely a few millions of years, which is extremely, extremely short compared to the lifetime of the Sun. Remember, the Sun is likely to live a total of about 10 billion years. So once again, we're looking at a factor of 1,000 difference in ages. And so as Eta Carinae was nearing the end of its life, it ejected a lot of material. And in that eruption process became much, much, much brighter, which is why it was visible and so bright in the night sky in the 19th century. And the image on the left is actually showing the ejecta from Eta Carinae. The surface of the star itself is shown on the right, or as close to a picture as the surface of the star that we have is shown on the right. And in terms of how intrinsically bright Eta Carinae is, its current luminosity is about 5 million times the brightness of the sun. So once again, think about it. 5 million times brighter. This is incredibly bright compared to anything we can imagine. Now, Eta Carinae is interesting, obviously, because it is a massive star located within a massive star-forming region within a star cluster. But this massive star is also in a binary. In fact, the star it is in a binary with is also a quite massive star that has a current mass somewhere between 30 and probably 80-ish times the mass of the sun. And depending on the models, even current research, trying to figure out how and why Eta Carinae exploded the way it did, some of those models have to take into account the presence of that close companion in order to explain that eruption. So that is once again an example of a star we've known about for a long time, and yet we're still trying to figure out how it evolved, how it influenced its environment, and whether the presence of a close companion actually played a role in setting its evolution. We're getting closer to having our full picture. We've talked about binaries within the galactic field, that is, binaries not in star clusters. We've also talked about young star clusters and some of the binaries within them, but we haven't really studied how those binaries and those clusters influence one another. And that is our next topic for the next few minutes. And in order to tackle that question, we need to move beyond the Milky Way. In fact, we're moving to the Tarantula Nebula, also known as the Turdid-Aratus region, which is located within the Large Magellanic Cloud. The Large Magellanic Cloud, or LMC, is a satellite galaxy of the Milky Way, which is quite obvious in the southern sky. And that galaxy in general, and Tarantula Nebula in particular, are the regions we know of that host the most massive stars we've ever observed. And some of those massive stars are located within the bright blue clump you can see at the center of this image. And so this cluster of stars is a newborn, very young cluster of stars. And you can see that those stars have started carving away at the gas. So all the whitish and reddish parts of the image in the outskirts, all of that is dense gas surrounding the inner regions of the cluster. And you can see that the stars themselves have pushed away and carved away at that gas. Once again, there are several very massive stars within that star cluster, and those stars are overwhelmingly in binaries. In fact, it is probably the best place to study massive binaries because there are so many of them in such a small region. But this is also one of the places where we have the clearest signature of how those binaries influence their surroundings. And specifically, those binaries influence their surroundings by pushing each other out of their birth cluster. This is a phenomenon known as runaway stars, which is illustrated in the plot on the right. So just to help you navigate this plot a little bit, the region in the bottom left of the plot is very, very similar to the picture I was just showing, with the bright, compact clusters of stars at the very center of this little square. The main picture is looking at a larger region surrounding the Tarantula Nebula, because the massive stars that this study focused on are massive stars that are currently moving away from the Tarantula Nebula. And so you can see from the arrows their direction of motion and the fact that they're all moving away quite fast from the center of the Tarantula Nebula. And this is a recent paper that was just published in the review Nature last month, which is studying those populations of massive runaway stars coming from this young massive star clusters. And most of the things we know can cause those runaway stars are actually caused by the presence of binaries. One of them is if you have a supernova in a binary system, one of the stars explodes, the other one can get pushed out of the cluster. If both stars were massive, that gives you a massive runaway star. The second one is something called few-body encounters or few-body dynamics. And we're going to watch this video probably twice just to give everyone a chance to figure out what is going on. But what happens in such a case is if you have a star that approaches a binary, the three stars will interact together due to the effects of gravity and will eventually settle in a configuration where two of them will form a binary and the other will get flung out at very, very large speed. So I'm going to replay this again. And you can see again this interaction between the stars that will result in a binary that is tighter than the original one, and one of the stars is getting flung out. And those interactions are extremely ubiquitous within star clusters because you have a very large density of stars. And so two things happen when something like that takes place. One of them is you fling out one of the massive stars, and so you remove it from the cluster. The other thing that happens is that you keep a binary, but this binary will tend to be tighter than the one you started with. The last way of getting massive runaway stars is intrinsically tied to the process of cluster formation. And so the video you're now seeing on the right is from my own simulations. So it is hot off the press. It was just accepted for publication 2 weeks ago. And you can see a cluster of stars that is forming from dense gas that is collapsing under the effects of gravity. You can see thousands of stars forming and pushing away the gas due to their radiations and winds. And you can also see several stars getting flung out of the cluster forming region. I'm just going to let the video replay once again so you can see the full picture. But the idea really is that you have those stars forming out of the gas. And as those stars are forming, they also grow closer to one another due to the effects of gravity. So you can see those little subclumps are all coming together towards the central region of the cluster. You can see some stars are already getting flung out in the early times, but as those clumps come together, you also get more stars that get expelled, and stars that get expelled at larger speeds. Part of that is due to the fact that you have more few-body encounters when your system becomes denser and when there are more stars. But part of it is also intrinsically tied to the process of cluster formation itself. And we'll revisit that in more detail on the next slide. I'm just going to let the video complete, and you can still see some of the stars moving away while some of the inner regions of the cluster are becoming denser and denser as the cluster finishes forming. Moving to the next video, we're now looking at the work of one of my collaborators that was also recently published. And in this specific study, we looked at the production of runaway stars specifically from the cluster formation process. This plot is slightly messier, so this video is slightly messier, so just to set the stage, all the teal blob essentially shows the distribution of the gas. You will see that it changes as the gas contracts under the effects of gravity. Most of the stars will not be shown, but you will see a cluster of stars shown as pink little stars, and those are the runaway stars themselves. And you will see throughout the video that those stars will form in the top left, follow the trajectory outlined by those teal lines, and eventually get expelled from the cluster. And that is a new mechanism to produce runaway stars that we've recently identified, which is the production of runaway stars through mergers of subclusters, or through the hierarchical assembly of star clusters. In other words, it really ties the production of runaway stars to the very processes driving the formation of star clusters, so tying it to gravity and tying it to star formation in a fundamental manner. We've just heard a lot about the interplay between binary stars and star clusters in young star clusters, but that is not the full picture. Star clusters grow older, and at this point, the interplay between binary stars and star clusters remains extremely interesting. And so the perfect location to study this is by turning our attention to old, dense globular clusters. And we have an example here of, in my opinion, one of the most beautiful clusters within the Milky Way, which is 47 Taucanae. And for globular clusters within the Milky Way, our telescopes are good enough that we can resolve many, many individual stars and study those individual stars within the cluster. Because globular clusters are so old, most of the stars within the cluster are low-mass stars. They are less massive than the Sun because those are the stars that tend to live for the longest. Any massive stars that were present within the cluster have long since ended their lives and turned into neutron stars and black holes and stellar remnants in general. But those stellar remnants can still interact with the stars within the cluster. And so what we're looking at here is an artist's impression of something called an X-ray binary. An X-ray binary happens when you have a neutron star or a black hole, which would be represented on the left, that becomes bound in a tight orbit with a star. As the two objects approach one another, the star can start feeding material to the black hole or to the neutron star, and that material will form an accretion disk. So you have material that is spiraling through the center and growing very near, very close to the black hole or to the neutron star. Because this is a phenomenon that is very energetic, those phenomena tend to create jets. So you can see the jet going from bottom left to middle right of the image. And that jet is caused by the accretion process and emits a lot of light in the X-ray band, which is why those are called X-ray binaries. And such X-ray binaries are extremely bright, and we found them in several globular clusters, several old, dense star clusters. And using X-ray binaries was in fact the first way in which we detected black holes and neutron stars within star clusters. We now have a much broader picture of black holes and neutron stars, though. And so the plot that we're looking at right now is our current family picture, so to speak, of black holes and neutron stars. The vertical axis is the mass of the remnant, so the neutron star or the black hole, in units of the mass of the Sun. And there is no horizontal axis. The black holes and neutron stars are just spread out so we can see them. The ones in yellow and red, which are labeled as EM black holes or EM neutron stars, EM denotes electromagnetic, which means that they were detected through light. In other words, they were detected through X-rays, X-ray binaries. On the other end, all the blue and orange dots, those are signals that came from gravitational wave emission. And so what happens with gravitational waves is if and when you have two massive objects that are spiraling together, they emit gravitational waves up until the moment when they merge. And the frequency of that wave depends on the orbit of the two objects. And so if I play this again, you can see those ripples in space-time coming from the gravitational wave and ending at the merger. And in the past few years, this is how we've detected most of the new detections of neutron stars and the new detections of black holes. In fact, we've detected them as they merged, as two black holes merged into one, or as two neutron stars merged into a black hole. One last topic I want to touch on very briefly before wrapping things up is the process of star cluster formation in the early universe. I've mentioned several times that the Milky Way and other galaxies host populations of globular star clusters, which are very dense, very compact, but also in most cases very old. They formed billions and billions of years ago. And very recently, using observations from the James Webb Space Telescope, it's been possible to start probing those clusters or similar clusters as they were when they formed or when they were very young, more than 10 billions of years ago. And so the two images that you're now seeing on the screen are both recent images taken with the James Webb Space Telescope of globular clusters as they were roughly 11 to 13 billions of years ago. And this is opening up an entirely new field where we can now start to compare computational models of massive cluster formation to some observations of those massive clusters as they were when they were newborn baby star clusters billions and billions of years ago. Obviously, those observations are not, you only see one point for your clusters, so you cannot see individual stars, but this is still orders of magnitude better than anything else we had before. And so, just to wrap things up, the key takeaways from this presentation, or at least the things I hope you will remember, are the fact that stellar clustering, whether it is just in the form of binaries or in the form of star clusters, is extremely, extremely common, both within the Milky Way and beyond. Most stars do not live in isolation. They have siblings, either a twin or larger and larger groups of siblings. And the fact that stars are in binaries and stars are in star clusters influence one another. And they have strikingly interesting implications for the formation and evolution of star clusters. Although that might in part be my bias speaking, I think this is a really new and exciting area to study now, especially since there are new gravitational wave detections coming in. There are new observations of massive clusters as they formed, and also a new generation of numerical models that can teach us a lot more about the interplay between binaries and their host clusters. So thank you very much for your attention, and I'm of course happy to answer any questions.
All right. Well, thank you very much, Claude. I have to say, I'm a little bit starstruck with all your wonderful binary talk here. It is one of my favorite topics, so I'm very, very excited to get a few questions coming your way from YouTube. So we're going to go ahead and transfer over to the question section. This is a reminder, if you're on YouTube Live, make sure to get your questions in so that we can ask them to our speaker. We've got all kinds of wonderful things we could talk about, but just to go ahead and start off with the first question here, we do already have a few in, so let me go ahead and start us off with first question from Enyo, asking about those for these binary star observations that you used, was any AAVSO data used?
I'm not sure. Um, so I'm personally not certain because I don't tend to work directly with observations. Most of my work is computational. And so when I interact with observations, most of the time I'm going to look at compilations of data that have already been processed. So I can't provide a more detailed answer. I'm sorry.
Oh, that's totally all right. I will just go ahead and say that, I think that it is very, very likely it was, given how much data the AAVSO has. And for any RASC members who are wondering, there's some wonderful stuff up on the RASC website about the AAVSO binaries and how to participate in observing. So super recommend. And a great Canadian resource for for binary stars. And really, really wonderful to see some of your simulations tie it all together like that. So just it looks like our second question is also from Enyo, and was about the animations. So are any of the animations available as a rotatable 3D video? This is a very detailed question.
Ooh. Um, so I know that some of it was processed as 3D, but not the specific animations I've shown. So, for example, the one I've shown from my own data, I can tell you for sure that it's not currently available as 3D. I've only made some videos, including the one I've shown. Um, for the one I showed just after mine, showing the runaway stars themselves, I know some data from those simulations is available as 3D videos on the Astronomy and Astrophysics website. So the scientific paper Astronomy and Astrophysics has some of those visualizations. All the other kind of more educational videos I've shown, all of those are publicly available, mostly from the ESO website, but they were designed as 2D. So yeah.
Wonderful. Sounds like there's some great stuff to go and download. And I'll just go ahead and say for folks who do want to try it a little bit themselves, there is also the NSTFM Gravity Lab, which will let you play with binaries and try your best to not make them runaway stars or whatever. So that will let you click on it yourself and like interact with it. So just as a little FYI. Now we have another question about. So this is very interesting. The one of the sort of famous stars are the. This is from looks like John's Garage. Are the Orion AE group stars gravitationally bound?
Yes, so they're part of the same star cluster, which means that they are gravitationally bound. Now, the boundary between what we consider to be bound in a binary versus what we consider to be bound in the star cluster, we could quibble, like, we could discuss the exact definition, but overall, the stars within the trapezium cluster are all bound together. It's just that pairs of stars and binaries are bound together much more strongly than everything else around it. And by much more strongly, I mean that if you calculate the gravitational potential energy within the stars, in many cases, the potential energy within two close stars in a binary is going to be as large as the entire potential energy of the cluster. So we're looking at orders of magnitude difference in how much they are bound, essentially. But yes, the entire cluster, or most of the stars in the cluster, would be bound. The big question for Orion and lots of young star clusters, though, is how much how much of the fact that they're bound comes from the gas, which is also massive and there. And so a big question in star cluster formation research is knowing what clusters will remain bound once they get rid of the gas versus which ones won't remain bound because the boundedness was in fact coming from the gas.
Oh, that's a great answer. So it looks like our next question is sort of a comment. CDB says, "Wonderful presentation, thank you." So it is a wonderful presentation. So thank you very much. I'm not seeing other questions, so I thought I might just sneak one of my own in here, which I always like to sort of put in. But given the uh, high proportion of interactions and runaways, have you done any or crossover with the what that means for planet formation in those systems?
Ooh, that's a good question. So, some of the work I've done with my collaborators a year or so ago was on disk survivability in young cluster forming regions. So, just to provide more context for the online audience, planets form out of protoplanetary disks, which are around the stars. Um, and of course, the big question when you talk about dense stellar systems and so on is wondering whether planets could survive around the stars. But a question that goes even before that is the question of whether those disks could survive long enough in order to form planets. Um, and so one of the big challenges again when you're in clustered environments is the very strong radiation fields, which tend to affect the disks quite strongly. So the stars get rid of their disks earlier than they would if they were not in dense clusters, which means you would probably have fewer planets that would form. Um, After that, in terms of survivability of planets, the question is essentially an extension of the one about binaries, right? Because it's still a matter of what kind of systems could remain bound or not. But because planets tend to be less massive than stars, well, are less massive than stars, the binding energy is lower. And so, what my work has shown is that dense, massive clusters tend to disrupt almost all binaries that are made up of two red dwarfs, and also a significant fraction of the binaries that are made up of sun like stars. So, in such systems, I would be very surprised if a planetary system was able to survive because its binding energy would probably be much lower. On the other end, if you're looking at systems like Orion, which are not quite as dense, not quite as massive, then it's certainly more likely that those systems could survive.
Wonderful. So lots of fun things for planetary scientists to look forward to as well. All right. Well, I think that's about all of the questions we have time for tonight. So we're going to go ahead and wrap up and thank our speaker once again. Thank you, Claude, and thank you for bringing a bit of star power to our last talk of 2024. I would be happy to stay on this topic for ages, but we do have to kind of wrap up. And just a little reminder, we'll be back in January of 2025. It'll be a whole new year, but this is the last one for 2024. So thank you once again for tonight. And let me go ahead and hand over to the president of Toronto Centre RASC, Tom Luton, to finish off the evening. Over to you, Tom.
All right. Well, thank you very much, Elena, and thank you very much to our wonderful speaker. And let's get on into the announcements. So, for those of you joining us here live on YouTube, welcome. This is one of two types of meetings that we have. You've just seen one of our speaker nights, and then in a couple weeks' time, we're going to have one of our recreational astronomy nights. For those of you joining us live, please say hello in the YouTube chat, enter some questions for presenters. If you're a new member of the Toronto Centre, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're coming from. So as Elena just said, there is no speakers night in December because of the holidays. So we will see you in the new year for our next speaker. As for our next recreational astronomy night, Wednesday, the 4th of December, 7:30 p.m., online only. So there will not be meeting at York University. Claudio Oriani will be talking about the sky this month, and Arushi Nath will be talking about using N-body simulations to analyze transit timing variations in multiplanetary exoplanet systems. So live here on YouTube. Immediately following this will be the 2024 annual meeting of the Toronto Centre of the RASC. So starting at about 8:30 p.m. on Wednesday, the 4th of December, will be the annual meeting. The agenda for the meeting, last year's minutes, the slate of council candidates, and the new bylaws that we are proposing are all on the website. You must register for this meeting no later than 12 midnight on the 2nd of December. If you did not receive an invitation and are a member of good standing, please contact me at president@rascto.ca immediately. So, with respect to the proposed bylaws, the creation of the Ontario Not-for-Profit Corporations Act has required that we make some alterations to our bylaws to reflect the new legislation. We've done so. We've drafted a new set, and we present them for your approval on the website. You will need to log into the website in order to read these new proposed bylaws, and then we'll be voting on them come the meeting. On behalf of the secretary, I am putting out the final call for nominations. For the first time in history, council has been unable to provide a complete slate, so vacancies for first VP and secretary were left. As a result, request to anyone of the membership who wishes to join council. Nominations are now being accepted for the open positions. And for any position you may wish to stand for. The member must be in good standing, and a nomination form requires signature of 2 additional members, also in good standing. The deadline is tonight, Wednesday, November 20th at midnight. Drop a line to secretary@rascto.ca with your nomination. Now, coming up in the next little while, we're having another Long Branch Park pilot project City Star Party. The first clear night of November 23rd, 24th, or November 30th to December 1st at 8 p.m. First clear night. Please check our website for a go, no-go decision based on the weather. Coming up at DDO on Sunday, the November the 24th, 12:30 p.m. is virtual Sunday sun gazing. Registration fee is as listed here, and you can register online at our website with the links at rascto.ca. Letting you folks know there is a council meeting on Tuesday, November 27th at 7:30 p.m. Members are welcome to attend. Please drop me a note, president@rascto.ca, for details and a link to the meeting. The Carr Astronomical Observatory is open. Operations are largely back to pre-pandemic conditions. We are still asking for masking in common areas, but the preference of the people actually in attendance will be taken. Please see the CAO bookings page on our website for all details. Reminder that the Toronto Centre runs on clean, renewable, volunteer energy. If you're a RASC Toronto Centre member and you're interested in helping out and you've got some free time on your hands, please contact Volunteer Coordination Team, volunteer at rascto.ca. And speaking of volunteering, RASC Toronto Centre is now working with Benevity to receive charitable donations. So if you're a volunteer and your employer has signed up to make contributions for charitable work, please let us know either at president at rascto.ca or treasurer at rascto.ca. And a reminder that the holiday season is upon us, and gift memberships for the Royal Astronomical Society of Canada are available at mempub@rasc.ca. You can sign up online or renew at secure.rasc.ca. And with that, I'd like to wish you all a very pleasant evening. Thank you very much for joining us. Please follow us on all the forms of social media that we've got listed here. Uh, Reminder that for those of you watching us live, if you've liked what you've seen, please like, subscribe, and hit the notification bell. Be safe. Keep looking up. Good night, everybody.